In this video we define enthalpy. Alright, the definition of enthalpy follows naturally from an examination of the first law of thermodynamics. Alright, the first law simply tells you that changes in the internal energy of a system are simply the balance of the energy transfer as work and the energy transfer as heat. Right, an application of the first law of thermodynamics to a constant volume process leads to the following expression. Because at constant volume there cannot be any expansion work, then what happens is that the change in internal energy has to be identical to the heat. And again, it's very important to denote there that this only happens when you're working at constant volume. Alright, so then it turns out that constant volume conditions are really useful to calculate changes in internal energy to a chemical reaction or any process. Okay, but the problem of these constant volume conditions is that they required specialized equipment. Right? Notice that you would have to run the chemical reaction in a place, right? In a system, in an experimental apparatus where the volume doesn't change. And that can be actually quite difficult to do and expensive and sometimes even dangerous, right? On the other hand, it turns out that most of the chemical reactions that take place in life, like in our metabolism, for example, those are not under constant volume conditions. Instead, they're actually under constant pressure conditions, right? So it would be very useful if we could somehow utilize this expression to be able to obtain a measure of the change in energy in a reaction or in a system, but not under constant volume conditions, instead under constant pressure conditions, because those are more common and also more difficult, more easy to use or easier to use. Okay, so that's actually what the enthalpy is going to allow us to do. We're going to simply define enthalpy, and eventually we will see that measuring the heat transfer under constant pressure conditions will actually give us directly what the change of enthalpy in a process is, and that is going to make our life much easier, as you will see. Alright, so let's define then a new thermodynamic variable, which is going to be enthalpy. And enthalpy is going to be very closely connected to the internal energy. As a matter of fact, the definition is such that the enthalpy is equal to the internal energy plus the product of the pressure and the volume. Right? It's not obvious why the definition should be like this, but eventually you're going to see that if we define the thermodynamic variable enthalpy in this manner, then at the end of our work, we're going to be able to do something very useful. Alright, so in chemistry, we're not interested in the absolute value of the enthalpy or the internal energy. Instead, we're interested in changes during a chemical reaction or any other process. Right? So what matters here is the changes. And that means that the changes to the enthalpy are going to be equal to the changes to the internal energy plus the changes to the pressure volume work, right? Or the pressure volume product. Okay, great. Now, what we're going to do now is assume that we're working under constant pressure conditions. And again, we're doing this because that's how normally life occurs, how much of the chemistry takes place. Again, that is under constant pressure conditions. So if we enforce constant pressure here, what we'll have is the following. Delta H is going to be equal to delta E. Then if the pressure doesn't change, this turns into the following, P delta V. And that pressure is actually an external pressure that our system is under. So we get here something that is P external delta V. Right? You can already recognize right away that that is a term that we have seen before, is somehow related to the expansion work that you can do in a process. Okay? As a matter of fact, what we can then do now is just bring in here the first law of thermodynamics and recognize that this is simply equal to heat plus work, okay, P external delta V. But of course, if we're working under constant external pressure conditions, then we actually know what the work, if there's only expansion work, what this term would be. Notice that this would simply be Q minus P external delta V. Okay, that is the work that you can do under a constant external pressure as long as the only work that you can do is expansion work. and then you will have that this is equal to P external delta V as well. Alright, so obviously these two terms cancel, and then what happens is that the change in enthalpy is equal to Q, and it's very, very important to, again, to note here that now we're under constant pressure conditions. Okay, so let's summarize here what we've done in this video. Delta H is a variable that we have defined as delta E plus delta PV. At first, it was not very obvious why we wanted to do this, but at the end, by application of the first law of thermodynamics, we've seen that if you're working at constant pressure, then what happens is that this delta H is equal to Q sub P. Why is this important? Well, this is important because measuring the heat, or the energy as heat transferred in and out of the reaction, working at constant pressure is very easy. Again, most of our experimental setups are under constant pressure conditions, not under constant volume. Right? So this is quite easy to determine, and notice that that automatically gives us the change in enthalpy in that particular system. Now, enthalpy and internal energy are not the same, but they are very, very close. Notice that the only difference is that delta H and delta E are just different by a change in the pressure times the volume, and that is generally going to be a very small number. Okay, so because it's generally much easier to work under constant pressure conditions, and then measuring the heat transfer under those conditions is fairly easy. When we talk about given chemical reaction or chemical system, we actually prefer to talk about the change in enthalpy in that chemical reaction or chemical process rather than the change in internal energy. It turns out that the enthalpy and the internal energy are going to be about the same. Those changes are going to be slightly different, okay, but enthalpy is much easier to determine, so that's why we prefer to use enthalpy, and we would prefer to use enthalpy from here on in our survey of thermodynamics. Okay? Right, so again, the take-home message here is that enthalpy is something very similar to internal energy, but it's much easier to determine, okay, because it's just the heat transfer at constant pressure, and that's why enthalpy usually is more used than internal energy to see how energy changes occur in a system. There's one final thing that we can talk about right here, and that is that this expression for enthalpy, if can be modified very nicely under ideal gas conditions. As it turns out, when you have liquids and solids, that term is actually very, very small. But for a gas, what you can do is the following. You can say, well, if I now have a gas, the idea is that I can apply the ideal gas equation, right, and change that into change in delta or nRT, number of moles R and temperature. Okay, and this is going to be something very, very, very useful to calculate for us. Okay, again, that's going to be our preferred way to calculate delta H, which you can do this way or that way, and again, this is going to allow us to do things very easily. Okay, one final note about the enthalpy is that enthalpy is an extensive property. That means that it depends on how large your system is. If this is a chemical reaction, it matters if you're starting the reaction with 7 grams of reagents or 100 grams of reagents. The change in enthalpy would be different. Okay, and that's something that is a little bit unwieldy, a little bit awkward in chemistry. We like to use intensive properties instead, right? So those would be changes in enthalpy that do not depend on how many grams of reagents you have. All right, so for example, molar quantities, we can define here the molar enthalpy simply as the enthalpy divided over the number of moles. Right, the units of these are now going to be joules per mole, and that is intensive, that is just per mole, so it does not depend on exactly how many grams of reagents or products you have. Right, so the intensive version of this equation will be simply the per mole quantities plus delta RT. We'll of course notice that with the way to change the enthalpy and the internal energy into molar enthalpy and molar internal energy is simply divided by the number of moles, and that's what we have done here. That's where you don't have the number of mole in this change in RT. All right, so in this video we have introduced the concept of the enthalpy, and we have seen that this is going to be a preferred way to determine thermodynamic changes into a chemical reaction or a chemical process, because it's far easier, far more convenient to use than the change in internal energy.